Okay, in this example, we are going to derive the cost minimizing input levels and the cost function for the Cobb-Douglas case. So remember, the Cobb-Douglas case, is a production function that looks like this. And to keep things simple, I'm going to assume that, of course, alpha and beta are non-negative, but also that alpha and beta sum to 1. Otherwise, the algebra gets a little bit complicated without really illustrating anything. Now, before I start the computations, let me remind you of a couple of things, which is the marginal product of capital, in this case, is just the derivative of the production function with respect to capital, is A alpha k to the alpha minus 1 L to the beta. And one interesting thing is that we can rewrite this as, think of passing the k to the minus 1 down, and then what you get is alpha q divided by k. What is q? Remember that q is the amount of the quantity produced, so this is also q. And by algebra, we can simplify that expression to that. And similarly, the marginal product of labor is equal to A beta k to the alpha L to the beta minus 1. And this allows us to write this as beta q divided by L. Notice that because it's going to simplify the algebra quite a bit in a second. Okay, so that's the Cobb-Douglas case. Now, we're interested in solving the cost minimization problem. And it's very easy to see that basically the solution is going to be interior because the Cobb-Douglas production function also, if you remember, has these isoquants that look like this. They asymptotically reach the axis, but they never touch. So the solution has to be interior because nothing gets produced at the axis. So what does that mean? It means that the cost minimization solution is characterized by the two equations that I gave you, which are one, that Q is equal to A k to the alpha L to the beta. That's just substituting the production function. And the second one is that the marginal product of capital divided by the marginal product of labor has to be equal to the relative prices. And using this, that is just equivalent to alpha L over K beta equal to R divided by W. Okay, it's a little bit of algebra in that step, but that follows immediately, and that is also equivalent to L equals to R divided by W beta alpha K. This is one equation that is going to be very useful, so let me take a moment to interpret it. Now, this is telling us that whatever the solution to the cost minimization problem is, the relationship between labor and capital is given by this equation. And let's check if it makes any economic sense. It's telling you that the amount of labor relative to the amount of capital, so if you wish you can pass the K here, increases with the relative price R divided by W. That makes a lot of sense. The more expensive capital is relative to labor, the more labor should be used relative to capital. And it also increases relative to coefficients beta divided by alpha, which kind of also makes intuitive sense. As beta goes up relative to alpha, remember that they are up to 1, labor becomes more important relative to capital and is used more. So that equation kind of makes intuitive sense. Now let's solve for the optimal level of inputs. So if we substitute 2 in 1, we get the following, which is Q equals to A K to the alpha, and now we're going to substitute L. So we get R divided by W, beta divided by alpha, K to the beta. Okay. And if you solve the algebra here and use the fact that alpha plus beta are equal to 1, So after some algebra, this is going to be equivalent to the K minimum level is going to be equal to Q divided by A times W divided by R to the beta and alpha divided by beta to the beta. So that's our first solution. That tells us what the cost minimizing level of capital is for any prices W and R. Now that we have this, we can substitute, let me call this 3, substitute in 3, and we get that, again, after some algebra that I'm not going to write for you, boom, 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 boom. We get that the L minimum is equal to Q divided by A, R divided by W to the alpha, and beta divided by alpha to the alpha. So now we also know what the minimum level of input is. The amount of labor that minimizes cost, is. We have fully characterized those as a function of the prices R and W. So the final step is we want to compute the cost function, what is the cost function of producing Q as a function of W and R, and that is simply going to be equal to R of K min plus W of L min, so we substitute those there, and if you do the algebra, which again I'm not going to do for us here, that gives you the following formula, which is Q times R to the alpha, W to the beta, divided by A, times this funny looking term, which is alpha divided by beta to the beta, plus beta divided by alpha to the alpha. Now if you're curious to what that terms look like, let me draw it there for you. That's a function of alpha, and when alpha and beta add up to 1, as we have assumed, that term, let me call it theta, that term theta basically looks like this. So because of the constraint, alpha can go between 0 and 1, and basically this theta takes a value of 1 here at 0 and at 1, and then is basically an inverted U shape that takes a maximum value of 2 at 1/2. It's a function that looks like this. It's just a constant that depends on the value of alpha. I want to do a few remarks to emphasize for you how much economic intuition there is in the solution to this problem. So the first thing I want you to notice is that the cost function is linear in Q. Remember also that the Cobb-Douglas production function, when alpha plus beta is equal to 1, is constant returns to scale. So that should be surprising that if you're following the intuition of what constant returns to scales mean, and this is a preview to something we're going to elaborate more carefully in the next section of non-example material, that there is a connection between the shape of the production function and the shape of the cost function. With constant returns to scale, it basically takes twice the amount of inputs to double the output. So you should not be surprised that it should take twice as much cost, that the cost should double, should be linear with the amount of output required. And this is exactly what we see. The second remark that I want you to see, and is extremely important, is that the cost function is not linear with either R alone or W alone, with the prices of the inputs by themselves. And the reason for that can be seen on this equation. And the idea is that as you change the relative prices, for example, by changing only one of the prices, the relative amount of labor and capital that gets used changes. In particular, for example, look at what happens when the relative price of capital is very high. Let's say when you're in a situation like this, that's the ISO cost line, you use a lot of labor and very little capital. When the relative price of capital goes down, let's say it moves like this, you stay in the same isoquant at the solution, but the relative amount of labor that gets used goes down. So what's going on here is that in the cost minimization problem, you can respond to the change in relative input prices by substituting away to the cheapest input. hope you see this, it's very important. You respond to substituting away to the cheapest input. And that allows the cost function to be nonlinear or sublinear, to be more precise in this case, to the relative input price. So for example, if alpha and beta are 1/2, the cost only increases to R to the 1/2 for R and W to the 1/2 for W. The final thing that I want you to see, the final remark, is what happens if you scale R and W by the same factor. Let's say you double them. Well, if you double both of them, the relative input price has not changed, so you cannot substitute away. So intuitively, you should literally double the cost of production. You have the same balance of labor and K, the same cost minimizing point, but since the inputs were twice as expensive, the cost should be twice as expensive. And that also follows for the formula. If you multiply R by 2 and W by 2, that the 2 filters out with an exponent of alpha plus beta, which is just a 2. So everything makes intuitive sense and have the properties that economically one would expect.